Hello there guys, welcome back to another epic inexorable maths video. In this video we're doing the Laplace transform of f of t over t, and we're going to show that it's equal to the integral from s to infinity of capital F of s ds, where capital F of s is just the Laplace transform of f of t on its own. So just for instance, let's say you wanted to find the Laplace transform of sine t over t. You would just integrate the Laplace transform of just sine t from s to infinity. That would be it. One thing I'll do though, for formality's sake, is I'm going to not call these s's, I'm going to change the variable. I'm just going to call them u's. Just because, guys, you don't want to be integrating a kind of function which uses the same variable as what's in the limit. It's just a formality, it's just a notation thing. But this is the same thing as the Laplace transform. And notice, guys, even though I've called these u's now, the u's will not appear in the final answer because they're going to get integrated away. They're just a dummy variable. Okay, so the way we're going to show this, guys, is we're going to start from the right-hand side, go to the left because it's easier. Let's do it. So we're going to start from the integral from s to infinity of capital F of u du. And I'm going to rewrite this as the integral from s to infinity of, and guys, what is capital F of u? Well, that is the integral from 0 to infinity of lowercase f of t e to the minus ut dt, and then there is a du on the end here because there was on the left as well. This is what we've got, guys. Now this is a double integral. Whoa, what's a double integral? If you know what a double integral is, happy days. If you don't, it's absolutely fine. It's very simple. Basically, we can't do much with this right now. However, if we change the order of integration, we certainly can. And we're going to use something called Fubini's theorem. It's not important if you don't know what it is. Not important. We're basically going to swap the order that we do the integration because it lets us do magical things. So we are going to swap the limits. We're going to swap the just the integrals around, and the kind of dt's and du's will also swap around. So we're going to write this as the integral from 0 to infinity, integral from s to infinity of capital F of t still, e to the minus ut, and now we're going to do du dt instead of dt du. Now guys, if you have seen double integrals, you might say, wait, don't you need to draw the region? Don't you need to see what you can't just change them? But guys, these are all constants. So you can, if you have constants in your limits when you do a double integral, you can literally just swap them around. The only problems come when you have functions in the limit, and we don't, because we're saying that s is a constant with respect to u and t, so it's just a bunch of constants. We can literally just swap the orders, it's completely fine. Okay, now why do we do that? Well, look at this, guys. Now that we've changed the order that we do the integration, we can actually integrate f of t times e to the minus ut, because we're integrating it now with respect to u, not t, so it's easier. So we can write this as the integral from 0 to infinity, and then let's actually integrate f of t, e to the minus ut, with respect to u. Now f of t is a constant, so it's not going to, nothing will happen, it's just f of t still. However, when we integrate e to the minus ut, it will actually become 1 over minus t, and then times e to the minus ut. So it's going to be a minus t on the bottom there, and then there's going to be an e to the minus ut, because guys, remember, t is a constant. We're integrating with respect to u. And then I will close that off, and I'm going to put my s and my infinity there, and I'm going to put my dt there, and then we're going to evaluate this. But before we evaluate it, let's just do a quick sanity check. Does it make sense that this is the integral of that? Yes, it does, because if you differentiate this with respect to u, what will you get, guys? The e to the minus ut, that will just become minus t e to the minus ut. The minus t will cancel out with this 1 over minus t, and you will be happy days. So that's all good, it all makes sense, it's perfect, lovely. Now guys, let's actually evaluate this. So this is the integral from 0 to infinity, and what happens when we put things in. So remember, we're replacing the u with an infinity and an s, not the t, because we integrated with respect to u. So if we replace the u with infinity, because t has to be positive, this has got to be constant divided by constant, lovely, e to the minus infinity, because t is positive, minus infinity times positive number, e to the minus infinity, guys, that is the number 0. So this will be the integral from 0 to infinity of 0, first of all, so I won't write anything because it's just 0. And then we're going to take away evaluating this thing at s. So guys, what is this at s? Well, all it is just the same thing. So it's just f of t divided by minus t e to the minus st dt. And guys, minus, what do you get? You get nothing other than them just cancelling out. And what's that, guys? What is that? The integral from 0 to infinity of f of t over t times e to the minus st. Aha! That is just the Laplace transform of f of t over t. And hence we've proved, let me get out of the way for you, hence we've proved what we've set out to do. So I'll just go up here because there's not much space below. Just to be really clear, that is equal to the Laplace transform. It's the definition, in fact, of the Laplace transform of f of t over t. So if you ever want to integrate the Laplace transform of f of t over t, just get the Laplace transform of the function on the top, f of t, and then integrate that from s to infinity. And now, guys, we're going to do a quick example. Let's do it right now. Okay, guys, the example that we're doing is the Laplace transform of sine t over t. Okay, so first thing, we need to find the Laplace transform of sine t. Now, you might already know it. I will just write it down. The way that you would find it, though, if you didn't know, is you could either use Euler's formula or whatever. I've got a video on it, link in the description. Why not? But let's write down the Laplace transform of sine t. So we know already that the Laplace transform of sine t is just going to be 1 over s squared plus 1. If you know it, you know it. If you don't know it, you don't know it. It's all good. If you're doing an exam, it's going to be on a table or something for you to look up anyway, but that's what it is. Lovely. Okay, now we need to integrate this. So we know that the Laplace transform, I've already written that down actually, so I'll just say that this Laplace transform sine t over t, this is equal to the integral now from s to infinity of this. Now, again, as I said at the beginning of the video, I could write 1 over s squared plus 1 ds. But because s is in the limit, I'm going to just change the variable. It's a dummy variable. It doesn't matter what letter of the alphabet I call it, so I'll call it u. So I'm going to say this is actually the integral from 1 over u squared plus 1, the integral of 1 over u squared plus 1 from s to infinity of du. Again, guys, the u's don't matter. The important thing is this is the same function as that. I've just changed the letter of the alphabet, but it doesn't affect the maths. Okay. Now, this ensures that our final answer will be a function of s, which is what we want. It's just the convention. Lovely. Now, guys, you might know that 1 over u squared plus 1 integrates to arctan. So this is equal to arctan u, and we're going from s to infinity. Now, guys, technically you're supposed to do limit as, make up a variable approaches infinity, and you're supposed to put that there. I've put infinity in the limit very loosely, guys, but like just you can follow what I'm saying, right? It doesn't matter. There's infinity in like up there. There technically shouldn't be one, but it's fine. It's fine. Don't tell anyone. Okay. Arctan of infinity is pi over 2. Again, I'm saying that very loosely. Arctan of infinity doesn't even make any sense. The limit as something approaches infinity of arctan of that thing, that's pi over 2. But anyways, doesn't matter, guys. Doesn't matter. Doesn't bother me. Anyway, sorry. Arctan of infinity is pi over 2. And arctan of s is arctan of s. So it's pi over 2 minus arctan of s. And that is our Laplace transform. So that's the Laplace transform there. Pi over 2 minus arctan s, that is the Laplace transform of sine t over t. And that's kind of how you use the formula and whatnot. Thank you guys, as always, so much for watching. I highly appreciate it. And I'll see you in the next video.